In this unit, we're going to talk about the concept of area. In particular, this video is going to look at the areas of rectangles and parallelograms. What I wanted to do at the beginning is talk about something that I feel is overlooked when you're first introduced to the idea of area. The definition. The definition of area is the amount of square units needed to cover an enclosed region. We're literally talking about the number of squares that it would need to cover an enclosed region. And in problems, we see all kinds of different units. We see square inches, square centimeters, square miles, square yards. Two in particular that I could actually show you in the video to scale would be a square inch and a square centimeter. Okay, so the first picture, I claim that that is a square inch. And it's a square inch because the sides literally measure 1 inch. We got 1 inch on that side. We got 1 inch on that side. And of course, because this will be a square, all the sides will be 1 inch. The other I claim to be a square centimeter. So I've got 1 centimeter by 1 centimeter. So when we make the statement that a certain shape has an area of 100 square inches, it means that it takes 100 of these to occupy the space. And if we say that a shape has an area of 1,000 square centimeters, it means that it's going to take 1,000 of these to cover that shape. Now, of course, you have all kinds of different units, but these happen to be the two that I could fit on paper. We also have square feet, we also have square yards, we have square miles, we have square kilometers, and so on. Example 1, we're asked to figure out how many square centimeters are needed to cover a rectangle with dimensions 4 centimeters and 6 centimeters. Okay, so what we're really doing here is taking a literal approach at looking at area. We're going to figure out how many square centimeters it takes to cover that figure. The number of square centimeters it takes to cover that would essentially be the area. Then based off of observing this, we should be able to figure out an area formula for a rectangle. Okay, so what I'm going to do first is take this rectangle and verify that it is 6 centimeters by 4 centimeters. Okay, so we've got the 6. We've also got the 4. In order to create the square centimeters, what I'm going to do is draw lines at every 1 centimeter. So I'm going to break up the sides in both directions so I can create squares. Okay, it's going to start off with me marking off at every centimeter. Okay, and then what I'm going to do is go ahead and connect across. All right, so each of these is going to be a square centimeter. Each of these little boxes is a square centimeter. We're asked to figure out how many square centimeters it takes to cover this rectangle. Okay, so if we count them up, we're going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. We have a total of 24. This is going to be 24 centimeters squared, and that's how we would write it with the units. However, for every rectangle that we come across, this procedure of dividing things up wouldn't make sense to do all the time. So we should be able to think of this as just a general representation of any rectangle. We can divide it that way and then think about, okay, well, how do we take the dimensions, the description that we had of the rectangle from the very beginning, how do we take those and calculate the area? And to do that, it would just be 4 times 6. You actually just take the dimensions that we have, and it sounds right mathematically. We basically have 4 rows of 6, or you can say that you have 6 columns of 4. So the product of the 4 and the 6 is going to give you 24. Now, we typically refer to the sides of a rectangle as the length and the width. Usually, the longer side is going to be called the length and the shorter one's the width. That is not a set rule, but in this case, we'll go ahead and let that be. This could be the length L. This could be the width W. So as just a general formula, for a rectangle, the area would be calculated by taking the product of the length and the width. Thinking forward about other shapes that we're going to end up studying, we have parallelograms, we have trapezoids, we got triangles, we've got kites, we got hexagons. For other shapes, it might not make sense to use the words length and width. Okay, for other figures, should be more useful to refer to perpendicular dimensions as bases and heights. We're going to let that be our consistency. For a rectangle, if we refer to it as a length and a width, that is completely fine. But you can also refer to them as a base and a height. A base and a height, for something to be a height, which is like an altitude, it just has to meet another side at a perpendicular. Okay, so the length and the width would fit a base and a height. Generally speaking, for other figures, we're just going to be using base and height. However, the area formula for a rectangle, if you want, you can actually change it to the area is equal to base times height. So if you choose to use length and width, that's completely fine. We accept that for a rectangle, but you can also refer to it as the base times height. All right, so next, let's go ahead and take a look at how we would calculate the area of a parallelogram. In a parallelogram, any side can be called the base. With respect to the chosen base, the height is the perpendicular measurement from the base to the opposite side. The key word here is going to be perpendicular. This is actually going to be the key to figuring out the area of any shape. When we start thinking about all the formulas we've seen in the past, or any of them that we're going to see as we go through this unit, the multiplication is going to happen between perpendicular measurements. Okay, if you go back to the rectangle, the length times the width, or if you want to call it the base and the height, those two met at a perpendicular. The definition of a rectangle is to have all right angles. So the perpendicular was already built into it. All right, so here's a picture of a parallelogram. The side lengths don't meet at a right angle. Okay, so if our approach at calculating the area here is to take what might be called the length and multiply that by the width, just multiplying two consecutive side lengths, you don't actually get the area. You actually get an area that's greater than what it really should be. Okay, so the key to this is to make sure that you're using perpendicular segments. Okay, so in a parallelogram, what we can do is add another segment, add an altitude inside of the figure that is perpendicular to one of the bases. Go ahead and let this be the base, just because of how I have the grid set up. And this would be the height to it. And that height is not the same length as the one that we have over here. That height is actually less than that angled line there, and you can easily prove that using Pythagorean theorem. All right, but what we really need to do here is figure out what the actual formula is. We do have a base. Let's just go ahead and put a B there to represent the base, and that's all the way across. You also have a height. All right, in addition to that picture, I have a second picture of that parallelogram. And what I'm going to do next is cut them out. All right, so here they are cut out. Now remember that these are identical parallelograms, which means that their areas are exactly the same. Okay, the areas are the same from one to the other. The first, I'm going to leave it just as it is. I'm not going to touch it, just let it be. The second, what I'm going to do is cut it apart. And I'm going to cut it apart in a very particular way so that I can move the two pieces around and easily calculate the area of that parallelogram. And as a hint, the only shape that I've actually demonstrated the area for so far was a rectangle. So what I want to do here is cut that second parallelogram so that I can move the pieces around and make a rectangle. And to do that, I'm going to cut along the heights. I'm going to cut it here. And one really important thing that it does for me is it creates a perpendicular that's sort of on the outside edge. You still got this piece over here, but I've got a perpendicular there like the rectangle. If I take this piece and move it to the other side, I get a picture of a rectangle. And I can calculate the area of that rectangle with length times width, or with base times height. And the important observation here is that the base that I have in this rectangle is the same base that I have in the parallelogram, because I literally took these 3 units and just moved it to that side. I filled in this space. So if these two figures are congruent to each other, or they were congruent before I moved that piece, what I did is I reallocated area. Okay, so if they started off congruent, they have the same area. And if the area of this figure is the length of that side, multiplied by the length of that side, and this side is actually just the height of the parallelogram, and this length here is actually just the base that we have there, then the area of a parallelogram is going to be base times height. With the key point that the height is not one of the sides, it is a segment that exists inside of the parallelogram perpendicular to a side. All right, so let's go ahead and do some actual practice problems. Example 2, find the area of this parallelogram. You've got 3 different dimensions identified here. You've got this length here of 5 inches. You've got that at 4.5 inches. You also have this at 4 inches. Okay, we got 3 things, but the area formula is area is equal to base times height. We don't need 3 values. We only need 2 of them. Okay, and the rule here is that the base and the height must meet at a perpendicular. That's the key thing, and that's going to be a key thing throughout every shape that we look at. So, the 4.5, you don't use it. You don't need it. It doesn't help. The base is going to be the 5. The height is going to be the perpendicular to that 5, which is the 4. Okay, so the area is going to be 20 square inches. That extra measurement, the 4.5 inches, is just a distraction. You need to be aware that the way you calculate area is not just to take 2 side lengths and multiply them. For example 3, we're asked to find the length of DE. We need to find the length of DE, and DE is located right here. So we want that measurement. Okay, that measurement is perpendicular to AB. It's perpendicular there, so we might already be thinking about area. And this is a parallelogram, but it's just positioned a little bit funny here. Normally what we would do is make DA or CB the base, so we'd rotate it a little bit, but it is a parallelogram. Okay, so if we had DE and AB, and we multiply those together, it would give us the area of the full figure. But we don't, because we're actually looking for DE. But do we have the area of the figure? We don't obviously see it printed anywhere, but if we did have the area, if we did have it, we could divide the area by AB, and that would give us DE. Okay, so what do we have? We've got a 13, which is that side length, and we also have another measurement that seems to be hanging out on the side here. We've got a 9. But notice, the 9 is perpendicular in a way to AD. Okay, that measurement of a 9, you could actually just bring it in, if you wanted to, just draw a line parallel. You could let that be a 9. You would get your perpendicular here, and given the 9 and the 13, you could actually calculate the area. Okay, the area is going to be 13 times 9, which is equal to 117. Okay, now, the figure is the figure. Its area is its area. So, if we let AB represent a base, we could say that 117 is going to be equal to 9.4 times the perpendicular to that, which is DE. And to solve this, we just divide 117 by 9.4. And we get that DE is about 12 point, we'll just go with 4, since that was 1 decimal. We'll go with 4. Units would be inches.
Wait, what?